Hello everyone, thank you for connecting.
Hello.
Hello.
Oh, I
Good
recognize
morning.
voices.
Hello.
Oh, hello, hello. So today we will do a quite relaxed meeting. We'll just chat about the um, possible research directions, and I suggest that during the meeting we will develop tentative plan of um, research projects. So the goal number one coming in the coming Thursday is to complete presentations on WASP skills, and I will try to cover as much as possible on the coming Wednesday lab. Uh, Please try to send the slides to my email before midnight on Fargo time on Wednesday night. So it is needed so that although we all sit behind computers, if everyone will start to share screen, it may create a delay, and it will be better if I will project all slides in a sequence, and you will just say next slide and explain what is there. Um, the remaining skills include the anions, cations, excited states for one presenter, spin polarized for another one, and what else is meeting? The K points, the dispersion. So I'll do my best to cover it in the labs, and during the lab, please try to feel, especially if your presentation belongs to these categories that have been not covered yet, please try to copy paste your steps during the lab into the PowerPoint, so it will be a draft of your presentation. The free discussion on the research projects will definitely not take all the time of our meeting. So I think there will be time left for the academic class material, and the academic class material is set up to go over the excited states and specific theories for excited states. Right now, we do not have yet enough background, so similar as we did for other theories, we cover some background nomenclature, and when these components are sufficient, then we are going to main theory and then consider applications. Approximately the same style will be used for the excited states. So for just a second. Good. So for the presentations, I do have several options from previous years, but they are very incomplete. The selection of the subjects for independent research projects is a very creative process, and if you do have in mind some specific research project that you are doing, you can just type it in. So I'm going to tell some stories right now, and then I will share a link to the Google document where we will place names nearby the subjects, or if there are insufficient subjects, then we will slides. We will type in your preferences. So I did send the link to this tentative document to everyone, and it is incomplete. I do see much more options, but we need to pencil approximate interests of class attendees so that we have approximate idea what we will be doing in the next 3 weeks, and I'm going to prepare instructions for the remaining 3 weeks based on your choices. So what I'm covering right now, the general direction can be chopped on based on the whether you want to characterize materials or molecules. For the molecules, the typical thing would be the catalyst, the reactions, molecular dynamics of reactions, and for the materials, it will be interfaces with possibility of adsorption or charge transfer. There are a couple of options that I didn't include, and I will cover them and maybe add as we go. But my main goal in this interview to learn about direction of your thinking. So in substantial part of the materials here, the idea is to consider the nanomaterial that is able to absorb or emit light on one hand, or on another hand to generate electricity upon photoexcitation. One of the options is to focus on the material of today, so-called perovskites, red halide perovskites, which combine properties of solid-state semiconductors and liquids. So by today, they are very quickly growing materials, providing record efficiencies of the photovoltaics, and for setting up a conversion of light into electricity, one does need to consider jump of an electron from one species to another one. And this is general motif for any photovoltaics, and in perovskite materials it could be a layer of this semiconductor and then cluster or layer of another material, for example titanium dioxide, which we were playing with in the class. For magnetic materials and for saving of information, for storage of information in magnetic way, one can replace one of the metal ions inside this perovskite onto iron or manganese, and then it will be holding all positive sides of this new material, as well as it will be responding to magnetic field. There is a very interesting project that we are not showing here. It is so-called holy graphene, and I think there will be a person in class who would be interested to pursue this direction. So, but I want to play a fair game and show it to everyone. So there is so-called there are two-dimensional materials, and first of them is graphene, and typically it is carbon sheet which is infinite in two directions, and in third it is terminated either by vacuum or by dielectric. But there are recent synthetic findings that by chemical etching of the holes in the graphene, one can modify its properties and make it very efficient sensor. So, for example, if it is cosmetic and medical applications, if a person is cleaning teeth and want to check the quality of the breath, then there are sensors which will analyze the content of the human breath. So they're very sensitive to small things, small components. Or we all know the fire alarm smoke detectors. So these sensors are based on the property that a material changes electric conductance if some molecule is adsorbed to the surface of a sensor. So if one adsorb this H2S, which is not doesn't smell nice in big concentrations, but in very small concentrations, this gold has affinity, or the holes in the holy graphene are able to catch the metal nanostructures from the colloidal solution, and then this combined structure is becomes very sensitive as a sensor, so it changes conductivity by orders of magnitude upon adsorption of small molecules. So to here one can add sensors. For the carbon nanotubes, there is something much more modern than I was declaring here. The carbon nanotubes today are tested to serve as a platform for quantum computers. So in case one absorbs the specific so I'm not introducing what carbon nanotubes are, but by their electronic properties they are dark, which means they happily absorb light, but they are very unhappy to emit light. So their HOMO-LUMO transition is not doesn't have oscillator strength, or oscillator strength goes to 0. But if one finds a way to chemisorb the specific sort of molecules, then HOMO-LUMO transition becomes bright. And more than that, this bright transition becomes a good source of coherent photons that are able to hold information, and these single photon emissions are currently being funded as and of a lot of interest across the world for quantum computing. The chiral catalyst and metal organic catalysts, it is not my specialty, but from year to year there are people who are taking this course from synthetic chemistry background, and the metal organic complexes with a metal inside and organic ligands outside, and with a little empty spot aside, can temporarily absorb small molecules, transform them, and then release. So if anyone in the audience is targeting chemical or pharmaceutical career, one can select this subject, and I'll try to provide models or have a discussion which will be beneficial in this direction. And one of the reactions, not chiral catalyst, but just simplest reaction, is oxidation of water by catalysts. Phospholipid bilayer, it is for those who are interested in some bio applications, and it is one of the smallest parts of the living cells that one can model. And in addition to this mentioned subjects, I would like to bring in possibilities of several reactions of explosion, explosives, combustion, and combustion. So for combustion, it means that you mix in the simulation cell fuel and oxidizer, not one molecule but several, and then during molecular dynamics you are looking how the oxidizer rips off parts of the fuel molecule and creates products. For explosives, one is looking for a compound that is being decomposed during thermal molecular dynamics, and there are some volatile compounds that demonstrate decomposition during 1 picosecond molecular dynamics, and it is something that one can do in during the class. In the previous years, there were a lot of successful projects where metal, like platinum or silver, was facilitating the decomposition or catalytic reaction of the adsorbed molecule, for example, the peroxide decomposition. And I'm slightly jumping between subjects. For sensors and for materials that demonstrate interesting electronic properties, today there is an there is a new wave of interest in two-dimensional materials. We already mentioned graphene, but in addition, there is a ruthenium Cl3, which is very, very promising for information storage. There is a bismuth telluride, which has the zero band gap, and one can operate, so it is magnetically sensitive material, and one can operate the states at the band gap by magnetic field, and very simple computations are useful for these materials. And yeah, and the third one is combinations of perovskites and two-dimensional layers. So if one creates a network of lead, iodine, lead, iodine, same as in regular perovskites. So I'm drawing a two-dimensional structure. And outside of the plane, there are long organic ligands to one and another side. These materials get an enhanced ability to control their color, and the excitation lifetime is substantially longer than for any other materials, and this is also one of the actively explored material of today. So if you are looking to do some project that can be converted into solid research in the future, those are good candidates. So I'm going to maybe type in this additional subjects in the list, and I invite everyone to type your names near the subjects, so that it is not the final solution. We can adjust, but this little interview is has to be done a little bit ahead of time. So I'm going to type options, and then if I will try to contact by voice to all class attendees and make a little personal interview about preferences. And it is very much encouraged to offer your own project. Just generally type which direction you are interested in. So these options are not mandatory. Okay. Do I miss anyone in among the names? Let me check who is on the connection today.
I think going missing.
Who? Oh, Gwendolen. Well, there is. Okay, and among those who, oh, Steven is missing. Steven is missing. Yes. Okay, Amir, what is your preference?
I'm thinking about this, but
just tentative. We can redecide because we will start it not tomorrow, but in a week, next Wednesday. But I need just to prepare. So
Among these topics, graphene with hole and also maybe carbon nanotubes make more sense for me, but I'm not sure yet. Maybe graphene with hole.
okay. Okay. Zhaofan, what are your preferences?
Can I choose the silver and the silicon interface?
Yes. And are you seriously intended specifically for silver and silicon, or you just generally interested in metal to semiconductor interface?
No, I'm just curious about the interface.
Okay. Okay, good. Thank you. Yang Chao?
Okay. The carbon nanotubes with a duct.
Okay. Yeah.
Yeah.
Okay, very good. Thank you. Mahek? May I ask what you're interested in at most? Hello, hello. If you're not sure, you may just share your general interest in certain, in one or other direction. Okay, the microphone is not, doesn't seem working at Mahek's side. Okay, we'll let's go to Mahek. Will tell later. Raju.
Dr. Dimitri, thank you. Actually, I am interested in metal semiconductor interface, but not from here. I'd like to choose from my own research topic.
Okay.
So I want to do with something like LLZO and lithium carbonate, lithium cobalt oxide, LCO,
Mm-hmm.
LICO.
Please,
No,
please correct.
no,
You can access it and correct.
Okay, Dr. Dimitri, thank you.
Can you type it right now in this document?
Yes.
I think it is solid electrolyte, right?
Yes, Dr. Dimitri. You're right.
Okay. Good enough. Salim?
Yes, I'm interested in photovoltaics, and maybe I'm not sure which one particularly, but I would go for perovskite quantum dots.
Okay.
Yes, thank you.
Yeah, I'll just make both. Arrow and type explicitly. Rebecca?
I was interested in the graphene with holes, but if that doesn't work out, I would go with metal organic catalyst.
Okay, excellent. I'll mark it as first choice and second choice.
Okay, thank you.
Steven?
I'm also interested in metal organic catalysts.
Okay.
And I suppose another choice would be the metal porphyrin catalyst.
Okay, very good, Yeah, I think we do have a good starting point. You may copy this document and save for your records, and I will also share it with everyone in class. Mahek, do you want to share your choices right now? If the microphone is not working, you can type it in the chat.
She's not here. She's not here, maybe.
Okay, but she no, she's here. She's typing in the chat line. Okay, well, Mahek, please. Oh, microphone is not working, but you can type your subject or just edit document and type what near your name, which subject you want to do. Okay, I will check if the document is changed later on, and in the remaining time, I will just chat a little bit more about our class material. File. Forcefully feed by where? Interface and environment. Okay, Mahek, thank you. I do see your choice right now, and if I think it is this one. Very good. So I was looking to academic calendar, and we do not have much time. So basically, we will be doing project in 2 weeks, and then maybe leaving 1 week to wrap up and explain. I will try to make connections and check if this diagram is relevant to each of the projects that you have selected. But I do see a connection that this diagram may help substantially. What were we doing last time? We looked on the DFT and different forms of the functionals, going to GGA out, with gradient corrections. And then we were going to generalize the protocol of how the orbitals are used in order to compose density. In the original approach, we just list pairs of orbitals with the same index, and index runs from first available orbital to the highest occupied. So we run over all occupied. In the more updated version, we were running over orbitals with non-coinciding indices, and the contribution of each pair of orbitals to the density is set up by so-called density matrix. Then we looked that this density matrix can be symbolically chopped onto 4 blocks. The block corresponding to occupied orbitals, which has diagonal elements for the ground state, the block for excited states, which will be populated if the system is in actual has been promoted to excited state, and the off-diagonal blocks that getting non-zero value if the system is experiencing the process of transition from ground to excited. And I believe the last slide we discussed was that the perturbations, the contributions, the changes to the total density upon interaction between light, we have direction of light, and then we have electric and magnetic field. Then this electric field changes in oscillatory way, and product of electric field times transition dipole operator is the measure of interaction between light and matter. So this term of light to matter interaction affects how much the transition density is being changed, and the transition density is linear in this term, and the occupations of the excited states behave as a second power of this interaction Hamiltonian measure of interaction. So since we are considering low intensity fields, the E times mu in second power will be always smaller than E times mu in first power. For example, 0.1 squared is smaller than 0.1, right? So due to this argument, one is in rigorous theories for excited states, one starts consideration from the transition density matrix rather than excitation. So we have finished at this point, and now we need to slowly go forward. Please let me know if you permit me to go further, if this little attempt to recall material from last week was going successfully. Is it okay to go beyond this point, and or I need to provide more comments on this subject? Okay. If anyone is not happy with this slide, please raise the voice. Okay. Either everyone approves or no one cares. So, what is shown? Which equation is shown in this slide? Let me invite you to look on this big matrix and try to provide interpretations. Raju?
Density matrix.
Yes, but can you tell more? Like, can you tell which elements belong to ground, which to excited, which to transition density?
Actually, it is written. The red box is ground. The yellow is ground to excited. It's a transition. The yellow and blue transitioning, and the fourth quarter excited.
Excellent. Thank you much. It's absolutely perfect and correct. So let's highlight it in green. So this slide does show mapping of the blocks of density matrix and explicit form of this blocks of density matrix. Why we need this? Because explicit form of these blocks is very exhausting. It's too many information. But we do need an example. I did type this equations just to this matrix in explicit form, just to explicitly show what is assumed under this notation. So in the ground state, only the diagonal elements in the red block are non-zero. In the Fairview option that I hope to show tomorrow, and that Mahek will show to everyone on Thursday, one can populate diagonals of this green block. And the theory that we will start very soon, it will be our last academic subject in this class, will be a theory for computing this blue and yellow blocks. So how the transition density forms if the model is being perturbed by oscillating electric field of certain frequency. So this verbal construction is a main task for remaining lectures, which will be in remaining academic lectures. So find blue and yellow for specific for provided electric field and frequency of electric field. So if you will shake the system with electric field of certain wavelengths, it will or it will not respond to such perturbation. and I think Salim will confirm this statement for sure, because to my understanding it is his main specialty in the lab, right?
Yes, I believe so, but I didn't hear the question nicely.
Just no. Right now, it's not a question. I'm just asking you to support me in this saying that
Yes,
depending on frequency of the incident light, system does or does not respond to the perturbation.
Oh yes.
Good.
I totally believe it.
Okay, thank you. And we are going to find the level of such response. So there is a next trick that we may feel not super comfortable, but this as humans, but the next trick shown in this slide is extremely useful and helpful computational pathway for programmers. So our goal is to find this ground to excited transitional density matrix. So density matrix is a matrix, but it is so much more comfortable to work with vectors. So we are going, not only we as attendees of this class, but everyone in the world who is studying excited state is adopting the following little mathematical trick. A matrix is considered in a vector form. So this element is here. Then this element is there. This element is number 3, and last element is at the end. So even if matrix is big, one can scan it row by column, each rows one by one, and save these elements into a vector. So why it is done? Because applied mathematicians, programmers, have accumulated so many standard procedures how to work with vectors, so it will be very comfortable to use this background. If any of you is planning to be involved in programming, you may have heard or you will hear that there are standard subroutine referred to as linear algebra packing, or BLAS, which is another implementation of which were all standard procedures of finding eigenvectors of a matrix, inverting a matrix, are standardized and optimized. And we are going to consider, not immediately, not necessarily today, but through several lectures, as our main problem of finding the transition matrix as function of incident light frequency in vector form by diagonalizing certain metrics. So in all our life up to this moment, we can in the oversimplified way tell that we were always diagonalizing Hamiltonian matrix, and our vector was always wave function. In the next chapter that we are about to start, the unknown vector will be not wave function, it will be density, transition density matrix saved in a form of a vector. And our practical goal is to find such matrix. By finding eigenvectors of that matrix, we will obtain this transition density. I'll write it down. Find a matrix so that eigenvectors will give transition densities. Okay. Now, a little bit more of nomenclature and notations. This notation of density rho superscript GE and rho EG is informative, useful, and helpful. But if we are going to derive a new theory and we are going to refer to these objects again and again, three symbols are probably it's alarm clock to finish the lecture. So this nomenclature, these symbols are too long for using in each line. And the community of quantum chemists who deal with excited states adopt the notation and call the transition from ground to excited X, like vector X, and transition from excited to ground vector Y. So in narrow sense, we need a theory that will help to find X and Y vectors as function of incident frequency. So I'm going to verbalize it once again. We will consider that atomistic model of molecules and materials are perturbed by external oscillating field. For some fields, this external, nothing will happen. System will remain in ground state. For another, system will come into a transition from ground to one of the excited states, or back from excited to ground. And we want to explore at which frequencies these transitions will be most efficient. So for symbols, for symbolizing these transitions, we are going to use symbols X capital and Y capital. So we are going to find a theory that will help us to find this X and Y. So it is about noon. So I suggest that our short lecture will be ending at this point. Unless someone wants to protest and wants me to speak longer. So please approve this so I suggest we complete the meeting right now. Everyone who needs to disconnect is welcome to do so. Rebecca, may I ask if you will be available this time on Thursday, or it still overlap with your other lectures?
Yes, yeah.
You will be available, or you will be not available?
I will be there.
Oh, you will join us. You will present online with everyone else.
Yes.
Super. I'm so happy. Okay. So then everyone is welcome to disconnect. I look forward to seeing you tomorrow 5 p.m. Fargo time for the last lab before presentations, and looking forward to see your slides and hear your presentations on Thursday. Done.
Okay, thank you.
Yep, many thanks. You too. I'll stay here just in case. Thank you. Just in case any questions pop up.
Thank you, Dr. Dimitri.
Thank you.